Continuing the discussion on heat balance, we looked at this one. Let's look at the average diurnal variation in local time of the net radiative heating, sensible heat into the atmosphere from the surface as the surface gets heated up, and the storage in the ground station. This was measured in Sharubra, Saudi Arabia, way back when. So comparison of the surface energy balance or the Rubal Khali in the Arabian Peninsula and Arabian Sea are shown here later on. The red and blue dots we had shown before are the ones. So you can see that at midnight the convention here is that the heating downward is negative and loss upward is positive. So the net radiative forcing is negative at this site during the night. As the sun comes up, the heating gets positive, more incoming short wave than the loss, and then it reduces with sunset and then goes back to net loss in radiation as well. During the day, so at night there is a net negative sensible heat, so the air is actually colder than the well, you can do T minus T, so the sensible heat is negative, which means it's downward, so it's heating the land, so air is warmer. And during the day the land is getting warmer and warmer, the air is getting heated up and rising and taking sensible heat with it, so there is upward sensible heat and then changes sign again after sunset. And the difference ends up being a storage term or the heating of the land. Okay, not all the heat can be taken away. Obviously, then it would be very nice. Land would remain cool, but if you try to walk bare feet in the desert, you're going to burn your feet because the land is getting fairly hot. If you compare the surface fluxes at these different places, so 17 degrees and 17.5 degrees north and 47 degree east and so on, those spots that we saw. So we are going from desert onto the Arabian Sea, onto the Bay of Bengal to see the contrast. So on the desert point you have net surface heating of 98 watts per meter squared, and almost all of it is going back out as sensible heat, whereas the 3 watts per meter squared are going into heating the land. Whereas if you go on the Arabian Sea, you have more net surface heating by radiation, because the cloudy skies and humidity make the outgoing long wave much weaker than incident short wave. So unlike here, you end up with a strong radiative heating, and obviously there is evaporation, evaporative cooling, so latent heat loss is almost half of it. Then there is the sensible heat becomes very small compared to on desert, which is a very nice contrast to remember. And of course ocean can take up a lot of the heat, so the heating of the surface here, which goes into balancing sea surface temperatures and setting up the gradients, etc. Vertical penetration of radiation is a term as well. That's 90. So you can see the contrast here. Over the Bay of Bengal, which is much more convective, you can look at disturbed and undisturbed fluxes. So this is from Jasmine, where you had convective activity or calm days. That's what this is about. It was done during the summer months, so you have active and break periods and so on. So during the disturbed time, you see that the net heating is reduced quite a bit, because you have deep clouds that are convecting and blocking sunlight, and you have a lot of heat loss from the surface, which means the ocean is losing heat, so you have also increased sensible heat compared to, let's say, undisturbed time when there is no convection and the winds are weaker, ocean is getting heated and so on. So lot of latent heat loss here, much larger than the undisturbed period, and there is the SH of rain that we talked about before. Okay, so this radiative balance in a column depends obviously on where you are, and the thing to remember here, since we are doing deserts, is that the desert has a very different heat balance. Okay, we can also look at the vertical structure of the desert heat low. We are looking at specific humidity, which obviously is relatively low even at the surface in terms of grams per kilogram, because it's a desert, and it decreases immediately above the surface and reaches the transition zone above which humidity is basically bone dry 0. Okay, whereas if you look at the potential temperature during the day, you have this unstable profile which creates dry convection, and then you create this mixed layer which is fairly well mixed, and then there is a transition to increasing potential temperatures. Remember, the potential temperature has to increase with altitude, right? But what is interesting here is at night time, when the radiative cooling term becomes dominant, then you create this very stable profile. So you cool the temperature, surface temperatures greatly, and the mixed layer temperature is almost the same as during the day. So you have created this stable cap of cold air trapped below warm air, so heavier air below lighter air, which is a very stable situation and makes mixing very harder. And we'll see that this can also decouple the mixed layer from the surface layer, because the surface layer has friction as the winds try to converge and rise in the plume. There is friction, so we will see how that affects the dynamic balance in this kind of situation where you have nighttime impacts on radiative cooling. Okay, so we'll see that in the diurnal divergence in the next podcast. Okay.